In question 1 we have a cyclist pedalling downhill from rest, reaching a speed of 16 meters per second at the bottom of the hill. The cyclist and cycle have a combined mass of 68 kilograms. In A part 1 we have to calculate the total kinetic energy of the cyclist and his cycle on the horizontal section of the road. Well, for this we use kinetic energy as half mass times speed squared. The mass of 68 kilograms, the speed of 16 meters per second, gives a kinetic energy of 8,700 joules. In part 2 we're told the cyclist has dropped a vertical height of 12 meters and we need to calculate the loss of gravitational potential energy. Well, for this we use change in potential energy is equal to mass times gravitational field strength times change in height. Putting in the values, the mass of cyclist and cycle 68 kilograms, this is the gravitational field strength, and a drop of 12 meters gives a change in potential energy of 8,000 joules. In part 3 we're told the cyclist does 2,400 joules of work pedalling down the hill. We're asked to account for the difference between the loss of gravitational potential energy and the gain in kinetic energy of the cyclist and bike. Well, the gain in kinetic energy is greater than the loss of gravitational potential energy. This is because of the work done by the cyclist. However, some energy is lost to the surroundings as heat due to work being done against air resistance and friction. The energy wasted is equal to the loss of potential energy plus the work done by the cyclist, that's the energy going into the system, minus the gain in kinetic energy, the energy that remains in the system. Putting in the values, they've lost 8,000 joules of potential energy, done 2,400 joules of work, and still have 8,700 joules of kinetic energy. This gives a wasted energy of 1,700 joules. In B, the cyclist stops pedalling when they reach the bottom of the hill and come to a stop after 160 meters at a constant deceleration. In part 1 we need to calculate the time they take to do this. Well, for this we can use the Suvat equations. The distance is 160 meters, their initial speed 16 meters per second, they come to a stop. We're not asked for the acceleration, but we are asked for the time. The equation we can use is s is equal to u plus v over 2 times t. Rearranging for t, we get 2s over u plus v. Putting in the values given gives a time of 20 seconds. In part 2 we're asked to calculate the average horizontal force on the cyclist and the cycle during this time. Well, for this we could find the acceleration again using Suvat and then using force is equal to mass times acceleration, or we can use energy ideas. And for this the work done is equal to the loss of kinetic energy, and this is the force applied multiplied by the distance. So we can say that the force is equal to the work done over the distance. The loss of kinetic energy is the loss of 8,700 joules over 160 meters, giving a force of 54 newtons.